Okay, I'd like to start by talking about a little bit more about capacitors and combinations of capacitors versus equivalent capacitance. So, for example, let's say I have two capacitors in series that are parallel plate capacitors that are separated by, that are each have a plate separation of d over 2, and I want to compare that to a single parallel plate capacitor with a plate separation of d. Which of these combinations of capacitors has a greater equivalent capacitance? Which of these capacitors, the first combination of capacitors or the second capacitor by itself, has a greater capacitance? Think about this. Okay, I've written a little bit more detail. I've called the two capacitors in series system A, the single capacitor system B. I've made sure it was clear that each has plate area A, capital A. Oh, well, sorry, too many capital A's. And each has the same plate area, and each has the same material between the plates. So, does the system A have a greater capacitance? System B have a greater capacitance? Do they have equal capacitance? Or does the answer depend on the values D, A, and whatever's in between the plates? So, you should stop and think about it and see if you can answer that for yourself, but I will go on. Okay, here I go. Capacitance in general for a parallel plate capacitor, remember, is E0 area of the plates divided by D. In this case, E0 and A is the same for all of them, so we can even simply give that a value of 1, or just say that the capacitance goes as 1 over D, because that's the only thing that varies here, is the distance between the plates. So the capacitance is equivalent to 1 over D, where for that's in system B, it's therefore, oh gosh, hold on. I guess that's fine. So therefore, C1, the smaller capacitor, goes as 1 over D over 2, and C2 goes as 1 over D over 2. If you don't like the goes as, we can just put in epsilon 0A and say that C, the capacitor in system B, equals E0A over D, and C1 is E0A over D over 2, and C2 is E0A over D over 2. Okay, so we know that the equivalent capacitance for system B goes as 1 over D, and the equivalent capacitance of system A goes as the equivalent of C1 and C2 in series. So the question is how do we do C1 and C2 in series? Well, remember that in series, the equivalent capacitance in system A is going to equal to, or 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. That's how you add capacitors in series. Just rewrote that a little neater. So the equivalent capacitance in system A, 1 over C1. Since C1 is 2 over D, then 1 over C1 is D over 2, and 1 over C2 is D over 2. And so that is D over 2 plus D over 2 is D, and that's 1 over the equivalent capacitance, so therefore C equivalent goes as 1 over D. So for system A, it's 1 over D, and for system B, it's 1 over D, so the answer is they have equal capacitance. You can go ahead, and if you don't like the approach that I took with it goes as or it's proportional to, that's really just also proportional to, then you can go ahead and put in the epsilon 0A's, and you'll find that in both cases, in system A, the capacitance is epsilon 0A over D, and in system B, the capacitance is epsilon 0A over D. When we add them like that. So now let me ask a similar question. Now what if I make the two capacitors in series a little narrower, a little closer together, and ask now which one has a bigger capacitance? The equivalent capacitor, the capacitance of system A or the capacitance of system B? Which has a bigger capacitance? So I would challenge you to answer this conceptually rather than answering it by calculation. So you should stop and think about it, try to answer it, and then look at my solution. Ready? Here comes my solution. System A must have a bigger capacitance. When the distance between the two plates in system A added up to equal the distance between the plates in system B, they had the same capacitance. Now the plates are closer together in system A, and the sum of those two distances are less than the system B, and capacitance goes as 1 over D. So as the D is decreased, right? We've decreased the D's in system A. We've decreased the distances. As the distance is decreased, then the capacitance is increased, right? Because C is equal to epsilon 0 A over D in general. So as D is decreased, therefore C is increased. So A should have the bigger capacitance. Let's go ahead and show that. Since 1 over C equivalent is 1 over C1 plus 1 over C2 for system A, then if I invert that, then C equivalent is 1 over C1 plus 1 over C2 as written. So therefore, C equivalent is equal to, and plug in what C1 and C2 are. Again, capacitance is epsilon 0 A over D. In this case, for system A, each one has a plate separation of D over 3. So I plugged that in. I've written out the answer. C equivalent in system A is 3/2 epsilon 0 A over D, whereas C in system B is epsilon 0 A over D. And this is, of course, assuming that they are vacuum filled or air filled, where epsilon 0 is the permittivity of free space. It doesn't matter what they're filled with, but the answer is A. A has a bigger capacitance. Okay, so now the obvious question is what if I put two capacitors in parallel? And let's go ahead and say those two capacitors have plate separation D over 2, same plate area, and compare that to a single capacitor with the same plate area and separation D. Which has a bigger capacitance, the two in parallel or the other one? Again, I'll give you a chance to think about it, and my answer is coming up. So pause it, otherwise it's coming up now. This one hopefully was a little bit easier. The answer is by a lot the parallel plate capacitors, because in this case the capacitance for each parallel plate capacitor, for each capacitor in the parallel, parallel plate capacitor, the two capacitors in parallel have a larger capacitance, a larger equivalent capacitance than the single capacitor, because each capacitor has a shorter distance between their plates, so each capacitor has a bigger capacitance, and then the capacitances add in parallel, they just add, and so it has an even bigger capacitance because we're adding two in parallel. So what I mean by that is, let's just go ahead and call this, let's go ahead and make them C1, C2, and C3. In general, C is epsilon 0 A over D, and so therefore C1 is epsilon 0 A over D over 2, C2 is epsilon 0 A over D over 2, and C3 is epsilon 0 A over D. So you can see that C1 and C2 have twice the capacitance of C3 by themselves because they have half the plate separation. And then in parallel, C equivalent of the parallel combination is C1 plus C2. In parallel, they just add, so you have even more. It's 4 epsilon 0 A over D. So the parallel combination has 4 times the capacitance of the single capacitor. So one more question. Let's go ahead and take a capacitor. Again, we'll just make it a parallel plate capacitor, and let's make it a plate separation of D. And let's insert, instead of a dielectric, I'm going to insert a conductor. We haven't really talked about inserting conductors, but I'm going to ask you to try to figure out what's going on if I insert a conductor. Let me insert a conductor between the plates. I don't want the conductor to touch the plates because if the conductor touches the plates, it'll short the plates and it'll no longer be a capacitor if the plates are shorted. I guess if the conductor touches one plate, it won't be shorted. But so let's go ahead and put a conductor between the plates and not let it touch. How do we do that? Well, there's a number of ways. One thing we could do is we could actually put some kind of plastic dielectric material in here and a plastic dielectric material in here. But I'm not going to worry about what the dielectric does. We're just going to have this sandwich with a conductor. Okay, so I've annotated a little bit. So ignoring the fact that I have some dielectric that's keeping the conductor from touching the plate, or just let's say the dielectric has a permittivity of 1, so it doesn't change epsilon 0. Does inserting the conductor between the plates without it touching the plates increase, decrease, or not change the capacitance? Think about this for a second, and my answer is coming now. What you need to think about is what a conductor will actually do. And a conductor, charges are free to move. So in a conductor, the charges are free to move. And so I guess there's a number of arguments. One is that you can say that, well, because we will we still will cause a polarization of charges in the conductor like you do in a dielectric, you would think, well, the conductor probably increases the capacitance. That is indeed true, but a way to see how the conductor increases the capacitance is not about the separation of charge that is induced. Well, it is about the separation of charge that is induced, but maybe for a different reason, because what the conductor does is it makes the larger capacitor, the capacitor with a plate separation of D, now into two series capacitors with smaller plate separations. So let me go to a new page. So on the left is my original capacitor. On the right, the equivalence of putting the conductor in there is like putting another plate and a conducting wire and a plate. So putting the conductor in there is like making it into two capacitors in series. It's a conductor, right? So the conductor is simply going to allow if you put a plus Q here, then the conductor will allow a minus Q to go there and a plus Q to go there and a minus Q to go there. So the situation on the right has a greater capacitance than the situation on the left. How do I know it has a greater capacitance? Because the plate separations all the plates have the same area, and the plate separations between the plate separations between the plates of the capacitor, the original capacitor, if it was separated by D, the two new capacitors are separated by less than D over 2, right? Because that conductor had a size. So this is going to be less than D over 2. So let's say that the conductor was 1/3 of the distance, then this is going to be D over 3, and this is going to be D over 3 because the conductor itself, I know it's getting a little hard to read, but that conductor was D over 3. And we already saw that two capacitors in series, going back, that two capacitors in series that had D over 3, that had distances that added up to be less than the distance for the original capacitor, had a greater capacitance. So in this case, if A has a greater capacitance, then in this case, the one on the right has a greater capacitance. Again, I think that the conclusion is obvious from our calculation over here, but what you had to recognize is that when you put the conductor between the plates, it just acts like it's making the capacitor into two capacitors in series. It acts like what you see on the right here. That's what you need to understand. It's not that you don't understand, but that's what you need to take away from this problem. Another question you could ask is, what happens if I insert this conductor, but I do lean it up against one plate? What if I don't have a way, what if I put it up against one plate? Then once I've inserted the conductor, what happens? Does the capacitance increase or decrease or stay the same? Well, hopefully it's pretty obvious from the discussion that the capacitance must again increase, because by putting a conductor in there, all you're doing is you're making D smaller. And since again C goes as 1 over D, you're making D smaller, and so the capacitance increases even if the conductor touches one of the plates. That makes me realize that I forgot to talk about one conceptual point. When I go back to the ones in parallel, one conceptual point here is that we said, well, more obviously, I think that the capacitance of the two in parallel is bigger than the capacitance of the one. The equivalent here, or the way to look at the equivalent capacitance here, is that we're increasing the area of the plates by putting two capacitors in parallel. It's like making the plate area twice as big, right? Because we're literally just putting charge both on, trying to find an arrow, putting charge both on that plate and that plate, right? So we've got twice the area to put charge on. So that's going to increase the capacitance. So even if they had the same D, this would be a bigger capacitance.